Hello everybody. For this video, let's go ahead and talk about one of the more important applications of eigenvalues and eigenspaces. Let's take a look at this particular example. Let A be this matrix 3, 0, 0, 5. This is a diagonal matrix, as we know from before, because only the entries on the main diagonal are non-zero. What's interesting about this one is let's go ahead and take powers of this matrix. So A squared is 3005 times itself, which is 3005. So when we multiply matrix multiplication, we get 3 times 3 plus 0 times 0, and then 3 times 0, 0 times 5, right? The standard matrix multiplication. And just to show you the pattern here, I'm going to write out exponents instead of the actual value. So instead of 3 times 3 equals 9, I'm just gonna go ahead and write that as 3 squared, and then the second entry on the first row is 0, and then 0 and 5 squared. You can of course check that on your own. So again, 3 times 3 is 3 squared, 3 times 0, and then 0 times 5 is gonna give us 0. 0 times 3, 5 times 0 is gonna be 0. 0 times 0, 5 times 5 is the 5 squared. Okay. Similarly, if I go ahead and try to calculate a cubed, well, that's just a squared times a itself, but we just calculated a squared, which is 3 squared, 0, 0, 5 squared. And that again, if I go ahead and multiply by the a again, we have the same kind of the concept, 3 squared times 3 plus 0 times 0, that's 3 cubed. And then 3 squared times 0, 0 times 5, that's just 0. 0 times 3, 5 squared times 0, that's just 0. And 0 times 0, 5 squared times 5, that's 5 cubed. So we get 3 cubed, 0, 0, 5 cubed. Let's just do this one more time just to humor me here. 3, 0, 0, 5 to the fourth power is a cubed times a. So a cubed we just did is 3 cubed, 0, 0, 5 cubed. And of course, we played this game 3 times now. We know that if I go ahead and make the multiplication, 3 cubed times 3 is 3 to the fourth power. 0 times 0 is 0. So we just get 3 to the fourth power here. And really simpler operation is going to give us 0, 0, 5 to the fourth power. And you can kind of see that in general, if we take the matrix A and raise it to the kth power, we simply need to raise the main diagonal to the kth power, and everything else is still 0, so we just leave it as 0. And this is not something you get with a general square matrix, right? There's no way you can square a matrix and simply square each entry of the matrix. So this is something more or less unique to diagonal matrix. While in greater generality, for any sort of n by n diagonal matrix, really of any size, if we raise that to the kth power, basically raising the entirety of the diagonal matrix to the kth power, that's the same as raising each diagonal entry of the diagonal matrix into the kth power. It's a very easy way to calculate the power of diagonal matrix. Okay. Now, previously, we have the idea of similarity. So now, if you have the matrix A that is similar to a diagonal matrix, that is, A equals to PDP inverse. Just very important relationship here. A equals to PDP inverse. That's our definition of similarity. If you have that, then what we can do is to raise A to the kth power, equivalent to raising PDP inverse to the kth power. And what we end up getting here is this, repetition of PDP inverse, just like this, right? That's what, n's power means. But then if I go ahead and rearrange these, right, by associativity, I can focus on these terms first. So P inverse times P, P inverse times P, and P inverse times P, etc. What I can see is that these are going to be canceled to the identity matrix. Oops. Be really simplified into the identity matrix. So I end up going away, and what I have is actually just going to be P d to the k's power P inverse. And we know the diagonal matrix can be calculated with an exponent just by taking the same exponent to each diagonal entry of these matrix D. So that makes this calculation a lot simpler compared to the calculation of A. Because again, A is just some random matrix A that is diagonal, that is similar to a diagonal matrix D. So the structure of A is a lot more free in some sense. Okay, so this is kind of the motivation behind finding A that is similar to a diagonal matrix D. Well, let's take a look at that. Diagonalizable. This is exactly our condition for taking A and finding a similar matrix to a diagonal matrix. An n by n matrix A is said to be diagonalizable provided A is similar to a diagonal matrix D. Okay, another way to say that, of course, is that A is equal to P d P inverse, right? That's our very definition of similarity for some diagonal matrix D and some invertible matrix P. Again, just a very definition of similarity. Right away, we have the diagonalization theorem, theorem 5.5. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. N linearly independent eigenvectors. So in other words, I need enough eigenvectors. So how do we define enough? Well, I need exactly the same number of columns of A as linearly independent eigenvectors. But this theorem not only tells you when is A diagonalizable, or exactly the necessary condition for A to be diagonalizable, it also tells me actually how to find the diagonalization of A. That's kind of nice. So this is a very important and strong theorem that we have to leverage. So moreover, if A is diagonalizable, right, that's part of the condition here. If A is diagonalizable, then of course A equals to P d P inverse. Again, that's just our condition. But the following two statements tells you exactly how we're going to find these diagonal matrix and the corresponding matrix P. So one, the diagonal matrix D, let me go ahead and highlight this. The diagonal matrix D have diagonal entries consists of the eigenvalues of A, including their multiplicity. Okay, so this diagonal matrix is the eigenvalues of A. On the other hand, I need the matrix P to have n columns of linearly independent eigenvectors of A. So that's why we need, quote unquote, enough eigenvectors, because I need to be able to form this linearly independent set, which becomes the columns of this matrix P. And we know we need enough columns of linearly independent vectors to form a matrix that's invertible, right? By theorem 2.8. And then here's the kicker. Here's the main thing that you have to remember, and we'll see this in the details in the next example. Each corresponding to the eigenvalue in the corresponding columns of D. So the way this works is that you actually have to write down the eigenvalues that you're using to create the matrix D. And we're going to pick column vectors of P in the same order as we pick the eigenvalues of D. Let's take a look at that in the next example, and then things are going to be more clear. Well, let's take a look. By the way, this is where you need to watch the video for 5.2, or at least understand the example that we did in 5.2, because, well, we're going to refer back to it. So here's an example from 5.2. Is this matrix A diagonalizable? Well, what we know from the example in the videos in 5.2, we saw that A has two eigenvalues, lambda 1 equals to 4, which has multiplicity of 1, and lambda 2 equals to 5, which has multiplicity of 2. And we even found the corresponding eigenspace of lambda 1 and lambda 5. Lambda 1 and lambda 2. Okay, and these are the result, and you can, of course, double check with your notes in 5.2. And the point here is that any vectors in these respective spaces can be a eigenvector, right? Corresponding to lambda 1 equals to 4 and lambda 2 equals to 5, except for the zero vector, right? The zero vector can never be a eigenvector. So here's the nice part about this, okay? Once you found all of the eigenvalues and once you found all this corresponding eigenspace, the diagonalization process is super simple. You just have to write down the things correctly. So the way we're going to do this is I'm just going to go ahead and maybe highlight this one here. Lambda 1 equals to 4 and lambda 2 equals to 5. And my D matrix, right, as you can see, this diagonal matrix D, because the diagonal entries are the only non-zero entries, I'm just going to put the eigenvalues on the diagonal matrix. As you can tell, there's 4 has multiplicity 1, 5 has multiplicity of 2, so I total have 3 eigenvalues, right, counting up to multiplicity. So I can actually just put these essentially however I want. So for example, I can put 4 here, 5 here, and 5 here. Okay, and from there, I get to pick the corresponding eigen vectors from each space. The rule here is I need to be linearly independent. So for example, for the first column of D, because the eigenvalue I choose is for lambda 1 equals to 4, I have to choose from a eigenspace corresponding to this eigenvalue. In other words, I need to pick something from here. Okay, and we've seen how we can pick this. We can essentially choose any value of x2, again, except for 0, and get a corresponding eigenvector. So for example, if I go ahead and choose, say, I don't know, x2 equals to 2, then the eigenvector I get will be -1, 2, 0. Right, so again, think about x2 equals 2, and then you distribute the 2, and you get these eigenvectors. Column 2, column 3 of D, I choose 5 and 5, of course, just because of the multiplicity. Here, I can choose, again, any vector in corresponding to lambda 2 equals to 5. But be careful, I have to pick values that are vectors that are linearly independent. So for example, I can't just take x2 equals to 2 and x2 equals to 3, right? So 0, 2, 0, 0, 3, 0. Those are not linearly independent. That's a no bueno. So the simplest way to do this is to basically choose a value for x2, and then x3 is 0, and then choose a value for x3, whereas x2 is set to be 0. Okay, that's the easiest way to do this. So for example, I can choose 1 and 0 there. So one of the eigenvector is going to be 0, 1, 0. And then I can choose, say, 0 here and 3 there. So it's going to be negative 6, 0, 3. We know these two are the basis of this null space, right? Because eigenspaces are null spaces of some sort, so the parametric vector form are linearly independent. That's why if I choose only the multiple of one of these vectors, I'm guaranteed linearly independentness. Therefore, I got my diagonal matrix D and its corresponding invertible matrix P. Okay. Furthermore, because of this P is invertible, and we know that columns of P are linearly independent, therefore, if we take these columns, they are a basis of R3, and by our definition, negative 1, 2, 0, negative 0, 1, 0, negative 6, 0, 3 forms a eigenvector basis of R3. Now this one is a little bit extra icing on the cake, if you will, to make a little connection from the previous videos, previous lectures, but still that's something that we can do. Okay, and here, this right here is called the diagonalization of A, this process of finding this diagonal matrix D and this corresponding invertible matrix P. These are called the diagonalization of A. Okay, now this process of finding this diagonalization is called the diagonalizing A. So just a couple of terminology purposes, not the most theoretically challenging thing here. Just kind of remember the wording here. Okay, now the last thing you should be doing, since this is still relatively new here, is after finding this diagonal matrix D and the invertible matrix P, you should double check, right? Theoretically, you should double check so that this A equals to PDP inverse. But this is harder just because your P inverse is difficult to find, right? If you recall from the chapter 2 stuff, finding an inverse of a matrix, anything that's bigger than a 2 by 2 is kind of tedious. So instead of doing that, the better way to check is to use AP equals to PD instead. In other words, multiply both sides by P. Okay, that's a much easier way to check just because you don't have to deal with inverses. So that's basically it for the diagonalization purposes. Okay. The last thing I want to do for this video is, again, to show you the flexibility we have to deal with this. Because what we can do is to really pick this diagonalization however we like in the process of, after the process of finding the eigenspaces. Because here, I choose 4, 5, 5, right? Just essentially how I found the eigenvalues. But there's really nothing stopping me from changing this up entirely. And actually, I'm gonna erase these as well. Okay, and for example, I want to pick 5, 4, 5. All right, just for the laws, right? Well, then the rule is exactly the same as before. Well, the 5 should come from the eigenspace corresponding to lambda equals to 5, lambda 2 equals to 5. And I can make up my choice here. Again, really nothing stopping me from using any meaningful linear combinations, right? The setting one of the x2 or x3 to be 0 just gave me easy and the most obvious way to create that linearly independent vectors. But again, I don't really have to deal with that if I don't want to, basically. Okay, but this time, just for the sake of example, I'll go ahead and just choose the most basic one here. So when x2 is 1, x3 is 0, 0, 1, 0. And then for the eigenspace corresponding to 4, again, is this one right here. and I can pick x2 equals to I don't know, -1, for example. Again, I'm just picking these just so I can, you know, come up with different examples here. So these are entirely your choice. So 1, 1/2, -1, 0, and the last one again from V5, I can do maybe 0, -1, whatever. It'll be +2, 0, -1. Okay, and again, once you make the choice, your eigenvector basis of R3 is excited as well. Okay, so once again, the point here is that you really have a lot of possibilities in your diagonalization process, right? The diagonalization of A really could come from a infinite amount of choices. Not only you have a choice in changing up the location of your eigen values in your main diagonal entries of your diagonal matrix D, you then can have infinite amount of choices of each of the eigenvectors that you picked corresponding to the order of your eigenvalues. Okay, just because again these have infinitely many choices, right? So everybody's diagonalization can potentially be different, but the theory tells us that you are going to make it work if you follow this choice of picking your eigenvalues, then follow that up by picking the corresponding eigenvectors to each one of these eigenvalues. Okay, and then same idea, your then eigenvector basis of R3 is essentially selected automatically, right, by your choice in P. Okay, one more time demonstrating that there's really an infinite amount of eigenvectors basis of R3. Okay, so that's it for this video. We'll try to keep it a little bit shorter so the upload issue is not going to be a problem. So stay tuned for the next video.